In this video, I am going to do an example of an ANOVA F test. Okay, so example, 3 10-week weight loss programs are compared in a clinical trial, low calorie, low fat, and low carbohydrate. For comparison, there is also a control group whose participants are only told they are participating in a general health study. 20 patients participate in the study, and they are randomly assigned to one of 4 groups. The table below summarizes the amount of weight lost in pounds by each patient over the 10 weeks. A negative number indicates weight gain. Assume the weight lost for each diet is known to be normally distributed. So what we're going to do is we're going to use an ANOVA F test and a significance level of alpha equal 500ths to test the claim that the mean weight lost for each diet type is not the same. Okay, so here you can see our data. In the first column, you'll see the first sample, and this is for low-calorie diets. So the first person lost 7 pounds, the second person lost 9 pounds, and so on. Then we see the second sample, and this is for the low-fat diet. And here you see 1 pound was lost by the first person in the sample, etc. Low carbohydrate is sample 3 with our 5 patients, and then we have the control, and you can see there was one person who gained 1 pound. So step 1 for our hypothesis test is we want to state the null and the alternative hypotheses. Before I do that, I just want to be very clear about what my notation means. So let mu1 equal the mean weight loss in pounds on the low-calorie diet. So that's for the whole population of all individuals who are on the low-calorie diet. Of course, we don't know what it is. If we did, we wouldn't be conducting this test. Let mu2 equal the mean weight loss on the low-fat diet. Mu3 corresponds to the low-carb diet. Mu4 corresponds to the control group. So these are all population parameters. Okay, and here we have the null hypothesis and the alternative hypothesis. For an ANOVA F test, your null hypothesis will always be that all of the means are equal to each other. So all of the population means are the same. The alternative hypothesis is that not all the means are equal. So what this means is that at least one, and possibly only one, of the means is different from the others. At this point, I usually use StatCrunch and look at the descriptive statistics in the box plot, which will help me figure out if the requirements for the F test are met, and will also help me calculate the F statistic and the p-value. In order to do that, I am just going to copy and paste my data. Here I am in StatCrunch. And the correct commands will be stat, summary stats, and columns. I'm going to select all 4 columns and compute. So let's take note of a couple things. The first thing I notice is that the sample means 6.6, 2.6, 3.4, and 1 are indeed different from each other. So my sample means are different. However, the question that we want to answer with the ANOVA F test is this enough evidence to suggest that the population means at least one of them is different from the others? Okay, so we want to see if we have enough data here in order to draw the same conclusion about the population. I also want to take a look at the sample standard deviations. Here you see for the low-calorie diet, the standard deviation is about 1.8. For the low-fat diet, it's 1.1, about 1.1, 1.5, and 1.2 for the control. So one of the conditions for using the ANOVA F test is that we assume that the populations all have the same standard deviation. We don't know the population standard deviations for these 4 groups. So instead, we can just take the maximum sample standard deviation, which is 1.8, and we divide it by the minimum sample standard deviation, which is 1.1, and we just make sure that it is not greater than 2. So if it's less than 2, we assume that these samples are from populations that have the same standard deviation. One other thing I usually do is I take a look at the graphs and I construct side-by-side box plots. In this case, I would just select all 4 columns and hit compute. And you can see the box plots here. Because these samples are so small, this doesn't really help me very much. However, if you have slightly larger samples, you can look at the box plots and you can check and that they appear to be roughly normal, meaning they don't have that you don't see outliers and you don't see skewness, too much skewness. In this case, we happen to know that the populations, the weight loss for the 4 diets are normally distributed, so we don't really have to worry about that. But I just wanted to show you that you can use graph, box plot, and then pick the columns to do side-by-side box plots and check for normality. So in step 2 of the hypothesis test, we're going to just check the requirements and verify the ANOVA F test can be used, and then we're going to find the test statistic. So here are the conditions that have to be met. First, we were given that the samples are random. We were also given that the samples are independent of each other. There are no matching or pairing between samples. So the person, a person who was on a low-carb diet is not related to any of the people in the low-fat or the low-calorie diet, in other words. The normality condition is met. So even though the sample size is pretty small at 5, we're told that the weight loss for each of the diets is normally distributed. And this is the step where I said you can also, if you don't have either of these conditions met, you can take a look at the box plot and just check that the box plots are roughly normal, so you don't see outliers or extreme skewness. Finally, are the population standard deviations equal? Well, we don't know what the population standard deviations are. However, remember that we looked at the sample standard deviations and the condition was met that the maximum sample standard deviation divided by the minimum sample standard deviation, which is approximately 1.6, is less than 2. So we can assume that this condition is met and that allows us, these 4 conditions allow us to use the ANOVA F test in our textbook. The next thing I'm going to show you how to do is to use StatCrunch to find the test statistic and the p-value. So I'm back here in StatCrunch and I'm going to use the commands stat, ANOVA in one way. And I'm going to click on the columns that I want, and all I have to do is click compute. Here's my technology readout, and you can see it gives me the means, and it also gives me the standard deviations again. I can see that the test statistic is 13.206349, and I can see that the p-value is very small. It's 1/10,000th. So according to StatCrunch, the test statistic is 13.21. In step 3, we ask what is the p-value, and then we should always try to interpret the p-value to make sure that we understand what it means. According to StatCrunch, the test statistic was approximately 13.21, which is quite large, and the p-value was less than 1/10,000th, which is very small, indicating that it is very unlikely, probability of almost 0, to get data like those observed, assuming that weight loss is not related to diet type. In other words, assuming that the population mean weight loss is the same across all diets. Step 4, which is the final step of our hypothesis test, is that we want to state the final conclusion and we're going to use a 500th significance level. So recall that the p-value that we found was less than 1/10,000th. And that is clearly less than 500ths. So since the p-value is small, we have enough evidence in the data to reject the null hypothesis and conclude that the mean weight loss is not the same for all 3 diet types. In other words, we can conclude that there is a relationship between the amount of weight lost and the diet type.